got about a quorum of about 10 people. Okay, welcome all of you. My name is Jules Damji. I'm the developer advocate here at Anyscale. Welcome to today's meetup. Delighted to actually have you here. Super delighted. So some of you actually can join us from far away, from East Coast, West Coast, and those of you who are in the different time zone. We're very happy to actually have you join us on our monthly cadence of these community meetups. These meetups are all about sharing. I think it's very important for us to share these meetups with you. And we are at Anyscale, and the team, OSS team, is very steadfast about community participation. So you are the catalyst for adoption. So we really believe that this is a good platform and a good forum for us to share what's actually happening in the community and who is doing what with Ray. If you want to give a lightning talk, do let us know, do let me know. Or if you want to give a regular talk, do let me know and we'll try to fit you in the schedule. We do these meetups once a month on the last Wednesday of the month. So feel free to send me an email at jules@anyscale.com. Again, we're counting on you to spread the word and adopt about Ray. So some housekeeping to get started. All your mics are muted, so we can't really hear you, nor can we actually see you. If you're having Zoom difficulties, put it in the chat. Feel free to put any questions that you have in the Q&A tab. Please make sure you put in the Q&A tab so that we can answer those questions after each and every speaker. That way I don't have to go up and down on the chat. So please enter your questions in the Q&A tab. So let's get started. Today's agenda, I'm going to just go through quickly some announcements that we actually have, some highlights about the Ray Summit, which we had about a month ago. It was quite successful. So I'm going to, share with you some of the highlights and probably ask our esteemed speakers to see what the impressions were and what the takeaways are and what they think they'd like to see next year. We have two great talks today. One about data transfer speed, comparing an ML application, comparing two stores, Plasma Store as well as S3 by Ankur Mohan, is Director of Engineering and ML at Capital One. And then we have my esteemed colleague from the Ray team. He's a committer and an old contributor of Ray's from the early days, Simon Moore, part of the Ray team. I met Simon about almost 2 years ago at the Ray Summit meetup, or the Ray meetup in Galvanize, where they had just introduced Ray Server 0.0. So he has been around for a while, so we're going to hear from a good part of that. So a couple of upcoming events, if you're interested to find out about the things that we actually announced, particularly at the Ray Summit, which we just call Ray AI Runtime Engine, that allows you to scale your simple models at a massive scale. We have a webinar which is going to be held on October the 12th at 11 a.m. Pacific time. So there's a link over there for you to be able to join and register yourself. This is a webinar that will be hosted by the creators of Ray Air, and with a couple of other people in there. So be sure to actually register that if you're actually interested in that. We have another meetup coming. October and November is kind of full of meetups which are coming up. This is an external meetup, which is going to be participated at San Francisco Big Analytics Data. We have 4 speakers over here. Stephanie, Mang, and Joe are going to talk about the 100 terabyte XO shuffle, which is part of the Ray data and part of the Ray 2.0, to how you can actually shuffle massive amounts of data before you feed into training or before you feed into distributed training. And then followed by a deep dive into Ray datasets given by Clark Zinhao. He's one of the creator of Ray datasets and a contributor. And he's going to talk about how you can actually use training and bad inference with Ray Air. So that's a meetup coming up on October. It's at San Francisco Big Analytics. Big meetup group, so do join us if you can. It's going to be in the afternoon, so hopefully you are in that particular time zone. And then we have another meetup follow-up a month after that at the San Francisco chapter of ACM. We have 2 contributors from the Ray team. We're going to be talking about a new toolkit called Ray Air that consolidates all of the native libraries together to give you a very easy way to build your end-to-end machine learning pipeline. So make sure that you actually attend that talk and learn a lot about what are some of the new things which are actually coming up. So those are kind of the upcoming events which I think are going to be good for the community to keep in mind. And again, these slides are going to be shared with you, so you don't have to worry about scrambling and taking pictures of that, but feel free to to register for these upcoming events. Now, just out of curiosity, I'm sure a lot of you, or if anybody actually attended the Ray Summit last year, it was a huge success. It was one of the first, actually, in-person meetup, in-person summit they actually had. We have had 2 virtual summits, and there's a huge difference between the camaraderie and the interactions when you actually are there in person. So it was actually great to see this particular summit. All the sessions, including the keynotes and all the Ray talks, are available for you on demand. So go to this particular URL, and I think you just have to register once, and you should be able to preview a lot of those. So have a binge this weekend instead of reading or binging on House of Dragons. This will be a good way to find out everything about Ray. So just to give you an idea, what I did was I was quite inspired and quite awestruck by the participation of the Ray community that actually came over from 22 different states and 15 different countries, and then we had about 650 plus attendees from both days, and it was really great to meet all of these people. I met them online on Discuss. I met them at online meetups, and meeting them face to face actually makes a huge difference. So I was very heartwarmed by the enormous participation and the energy of the participants who actually came over there. And there was this feeling, there was this feeling of the Ray global community. And we were delighted to see people who say, oh, we've been talking about Ray in Colombia. We've been talking about Ray in Japan meetups. We have a Los Angeles presentation on Ray. There are a couple of meetups in Boston that talk about Ray. The China actually had a week-long, a couple of days summit a week before we had our summit, and they actually had a huge audience over there. Toronto is another place where people are actually talking about Ray at the MLOps conference. So we're beginning to see an emergence of the Ray global community, which is actually very heightening. So what I did was I sort of created my own impressions and highlights about what I thought was worthy of mention. And I think one of the things that was ubiquitous across everything was scale, right? Ray is all about scaling your machine learning workloads in Python across. And I think Robert did a very good job in articulating the 3 or 4 pillars, which were the emergence of Ray 2.0. One was it's faster, it is simpler, it's easier to use, and it's production ready. And Robert spoke about all these particular themes and actually pretty much corroborated by doing a 10-minute demo by building an end-to-end recommendation system using Ray Air. And I think that was quite impressive, even though it was just one Python file. There were other components of it which were built behind the scene. But this actually gave you an idea that Ray 2.0 has actually come a long ways from the early days where we had a lot of native libraries that allow you to do the same thing. But the faster and easier theme allowed people to somehow use these Ray Air APIs together to be able to build end-to-end application within one file, within one platform. So I think that was definitely the takeaway. And I think another thing that actually really inspired me was that, hey, quantum computing is here, right? We had Dario Gila, the head of and VP of advanced research at IBM, actually talk about computing, talk about quantum computing. And I've never seen or never heard somebody so simply articulate the concepts of what actually constitutes and what actually makes quantum computing so much easier. So it was great to actually see him make a quantum leap by linking, saying we're actually using Ray along with our QuizBeat SDK to submit massive jobs to the quantum server. So that was definitely a revealing and inspiring thing that, future is here really, and Ray is actually participating in part of that. Another revealing part was when Greg Brockman, the co-founder and CTO of OpenAI, revealed that they actually considered quite a few distributed computing systems when they were actually building and scaling machine learning language, and they settled on Ray to build some of their large language models. So that was actually quite heartwarming to see Ray being used at scale and somehow corroborated some of the themes that we were actually trying to communicate to the community, that Ray is about scaling. And even Ion Stoica asserted the same thing, that Ray allows you to scale your machine learning and Python workloads. And then finally, good to hear from the director of ML engineering, Smita Shyam from Uber, who shared how they're actually using Ray in their production to scale some of their, ETA or Uber Eats or ranking applications using actually Ray. So all these were quite heartwarming and all spoke to the themes that we actually wanted to articulate at that particular summit. Another interesting thing that actually emerged that we actually found out was how companies across the world who actually participated at the Ray Summit are using Ray at the massive scale. Now, Ant is probably one of the largest, one of the largest contributors for Ray, but also one of the largest deployment of Ray. They have about 450,000 cores that actually use, and these massive clusters sort of scales the application from online running to fraud detection to financial decision making. So this is really a massive scale, and they've achieved quite a bit of it. And we were actually very honored for them to actually share with us. And Shopify was another company that has built the entire ML infrastructure platform on top of Ray. In other words, they have data scientists that don't know anything about Ray, but they're using Merlin in order to abstract away all the intricacies of Ray. And this allows them to be able to move from not only TensorFlow, which was limited to the earlier implementation on Google Cloud, but now after adopting Ray, they can actually use multiple frameworks. They can use TensorFlow, they can use XGBoost, they can use XClearn, they can actually use PyTorch, and that sort of unleashed some of the other use cases that they couldn't actually do it. So that was quite interesting to hear from Isaac how they actually built this particular ML platform on top of Ray as an infrastructure to scale and unleash some of the use cases. And Instacart, those of you actually familiar with, and those of you probably used Instacart quite a bit during your lockdown, they use, again, Ray as part of scaling their scheduling and delivering ETAs, and they discovered that they could actually train 1,200 models from days within hours. So you had people in companies and different use cases across the company that actually do that. And Amazon is one of the one that actually uses, again, Ray at a massive scale where they can process terabytes of data a day, and that helped them reduce the cost as well. And my favorite, because I'm a football fan and I go to the World Cups every 4 years, it was heartening to see actually the FIFA World Cup 22 organization worked with the Qatar Institute, and they started sort of simulating what were the worst case scenarios if there were traffic problems using Ray and RLib. So I thought that was one of those projects that was quite personally appealing to me, because I'm a big football fan and I enjoy watching football. So this was actually quite hard for me to see. So these were some of the use cases that were presented, and there were many companies, notable companies, who were actually using Ray at scale that were there. So have a go and listen to any of these presentations that you actually have. And some of the highlights that I thought were interesting, that you might be interested if you were interested in Ray and how they actually, what are some of the 2.0 features that actually came out, are some of the talks over here, which are listed in that particular slide. And you can actually just go and link them and find and listen to them. You're going to hear something about Ray's serve today from Simon. So these are some of the talks that I thought were related to Ray 2.0 and deep dives into Ray, and that would be worthy of knowledge to imbibe in. And then a few talks that I found were interesting at how actually Ray is being used at Uber to do hyperparameter tuning at mass scale. Again, I mentioned about Merlin being used by Shopify. There's Spotify actually using it, and then the large-scale distributed training using TorchX with Ray was another interesting talk. So those were the things that I thought were fascinating for me. Now, what I'm going to do is I'm going to probably ask my guests over here, Ankur and Simon. Ankur, what do you think your highlights were for the particular talk? What did you actually take away from it? And then if you're going to come next year, what would you like to see more that you didn't see this time? Not to put you on spot, but I thought I would just put you on spot anyway.
Yeah, no, absolutely. So yeah, thanks, Jules. I've been a user of Ray for a couple of years now, and so as Jules mentioned, I'm the director of engineering at Capital One. My team is building a machine learning platform, and I'll be talking about some work that I've done a little bit later. But this was my first time attending the Ray Summit, and first of all, it was really great to attend a conference in person after like 2 years of just being virtual all the time. And I had seen Jules on LinkedIn, and I'm a prolific issue raiser on Ray's GitHub repo, and it's very heartening how quickly my issues get responded back. So I had communicated with a bunch of Ray developers on GitHub. So it was really good to meet them in person at the conference. And the community engagement that I observed was really incredible. There were like developers from companies big and small. There were a lot of university students and professors. A lot of the talks that I attended were standing room only. So that was really awesome to see such a strong community engagement. There was, as Jules pointed out here, a diverse set of companies, again, large and small. I think that speaks to the growing ecosystem and adoption of Ray. And what I found particularly heartening was that the new features that have been added in Ray 2.0 were exactly the type of things that I would have liked to see, which tells me that the company has a really good pulse on what feature sets, what are the pain points with machine learning development, particularly scaling machine learning workloads. And they are adding features that really address many of those pain points. So I think Ray is really making great strides forward. And I'm excited to be a user of Ray, and looking forward to seeing where the product goes. So
well,
I really enjoyed the
much.
conference. Yeah, in terms of talks, like I particularly, the Fred Reese's talk on zero copy model loading was just eye-opening. To have like 7x performance improvement with just a couple of lines of code. I'm a heavy user of Kubernetes, and Kubernetes is a very complex platform. Ray is a very complex platform. Having both of them work together in a way that just works out of the box is a very difficult problem to solve. And the KubeRay project that Ali Kanso from Microsoft and somebody from ByteDance demonstrated, that was really incredible. And I've used that in my project that I'll be talking about. So that was really awesome. And then the magic of Merlin, like how Spotify is using Ray for their Merlin platform, that was also really illuminating. So those were the 3 talks that I enjoyed the most.
Well, thank you very much, Ankur. Just for the record, I didn't pay Ankur to actually endorse those things. This was actually right from his heart. So that's very heartening to actually hear that. Thanks a lot, Ankur. Simon, I know you're an old geezer. I don't mean literally, yeah. but you've been around with the Ray from very early days, so you actually seen its progression from 0.8 to what it is today. And so, what were your impressions? I'm sure you actually met with a lot of people in that you can just give me a quick rundown of what you felt.
Well, it would be short. My biggest takeaway is actually, it's very impressive to see how Ray is used in the real world. And actually, this Ray Summit has been the first time, for example, we have heard from OpenAI and from Uber and Shopify publicly talking about exactly how they're using Ray in such a precise detail. So now you know every time, for example, when Uber is giving you an ETA prediction, well, it is the model is trained and powered by Ray. Right? Or when Shopify is recommending your product or there's some product tagging is there, you know, oh, wait, it is powered by Ray under the hood. So that's quite impressive and very, very, very much exciting to see.
Well, definitely. Thank you. Thank you for this endorsement as well. I think just to move on, if you actually want to get involved, just go to our Ray community and join our GitHub. You can actually give us a star if you're generous enough. File the bugs, file an issue, file your first issue that you actually want, pick up one of the first issue that you actually want to start, file a PR. We are very eager to get your PRs and get them incorporated. There's a discussion forum that actually is very lively with all the committees and contributors giving and answering your questions. So you can actually join us and discuss forum. We actually have a Slack is another form of communicating with the community. So the community is actually growing on a daily basis. We have a monthly newsletter to find out and keep you abreast about what's actually happening. And obviously follow us on Twitter. And that is kind of in a nutshell how you can actually get involved. And I think as part of a code of conduct, I'm obliged to actually put this slide up. And just to give you a TLDR, you know, our Meetup is harassment free. It's a place for everyone, regardless of who you are. And we believe in respecting and no profanity. So I'm not going to read each and every point. So I'm just going to keep the slide up for maybe about 15 seconds for you to somehow scan it or take a picture of it. But just do be polite when you're actually asking questions or if you're presenting. We do believe that this is an important part as code of the conduct. Okay, having said that, I think I'm going to stop sharing and I'm going to hand over the realm to Anku, who is going to be our first speaker, and he's going to talk about some of the work that he has been working at Capital One. So Anku, it's all yours, and I'm going to unmute myself.
Can you guys see my screen?
Yes, we can. Yes.
Okay, awesome. Okay, thanks, Jules. Yeah, so my name is Ankur. I'm the Director of Engineering at Capital One. My team is building a machine learning as a service platform. The work that I'll be talking about here is all of my personal work is not connected with anything that I'm doing at Capital One. I've been a user of Ray for a couple of years. I love the product. It's pretty awesome. I've actually learned a lot about distributed computing principles as I've been using Ray. And also I have a slight cough, so apologies if you hear me coughing. I will try to cover the mic the best I can, but just wanted to say that. Okay, so let me get started. So in this presentation, I'll be talking about the issues involved with scattering data from a managed object store, such as S3 versus the Ray object store. Now, why is this important? This is important because reading data is the first step in any data processing pipeline. And furthermore, in pipelines that contain map tasks, that is tasks that perform a repeated operation on the same data or shards of data, the data must be efficiently replicated across the compute nodes where the tasks are running. Otherwise, some tasks will just be waiting for the data to become available, which will limit the benefit of parallelization. And by the way, I should just say, I'll be reading from a script because I have a tendency to get long-winded, and I want to make sure I stick within the 40-minute allotted time. Okay, so in this presentation, we'll cover the following topics. I'll start with showing a test application that applies a speech-to-text model to a large number of audio files in parallel to produce transcriptions. These transcriptions are then input to a named entity recognition algorithm, which tags the entities in the transcribed text. So things like names, dates, places, etc. Now, the application of the speech-to-text model to audio files is an embarrassingly parallel task because the model can be applied to each audio file in parallel on multiple actors. However, to do so, we need to load the speech-to-text model first, which is about 600 megabytes. And this model must be replicated to all of the actors where the transcription is being performed. And how to do this replication efficiently is the focus of this talk. And then following the demo, I'll quickly go over how the test application is architected. I'm not going to spend too much time on this, although there is a lot of learnings that can come out of that. If there is time left in the end, then we can talk more about the architecture. Then quickly go over some Ray concepts such as actors, tasks, object store, etc., that you are probably already familiar with. And then this background in place will transition to the main focus of the talk, which is the detailed analysis of the various options for transferring data from S3 and then replicating this data across object stores. And then we'll conclude with the key takeaways. Right. So this is the test application workflow. As I said before, the test application applies a speech-to-text model to a large number of audio files in parallel to produce transcriptions. These transcriptions are then input to a named entity recognition algorithm, which tags the entities in the text, things like names, dates, etc. The application itself is structured as a multi-layered producer-consumer system. There are 3 layers, as you can see here. Layer 1, a data producer reads the S3 paths to the audio files and places them on a queue, marked Q1 here. Then in layer 2, multiple speech-to-text actors consume from this queue, download the audio files, and apply the speech-to-text model to the audio files to produce transcriptions, which are then placed on another downstream queue, shown as Q2 here. And then in layer 3, multiple named entity recognition actors apply an NER, named entity recognition, on the transcripts to label names, places, dates, etc. And this annotated text is then placed on the third queue, which can then act as a producer for further downstream layers. And I can try to play one of the audio files just so you can see what this sounds like. I'm not sure this will come through, but I'll try it anyway.
His wife now lies beside him, and the white shaft that marks their graves gleams across the wheat field.
Yeah, so these are like roughly about 15, 20 seconds long, and it's just like generally somebody reading a body of text, like a small piece of text. That's what the input to this system looks like. All right, and this video is like shows the demo running live. And again, like if there is more time in the end, I can actually show you the actual demo running live. But this is, I just recorded a video just in case something goes wrong. So you can see the label transcribed text is being displayed on a HTML text box in a live stream, and the parts of speech like person, time, etc., are being annotated. These annotations are being produced by the named entity recognition algorithm. All right, so moving on. This is the screenshot of the Ray dashboard. So you can see the speech to text actors running. Some of the other actors, like the named entity recognition, somehow don't show up, and I think that is a bug in the Ray dashboard. This is the system architecture. I'll just like talk about it like very quickly at a high level. So the main components are what are shown in this light purple. So this runs on a Kubernetes cluster that is provisioned by kops, which is an open source set of scripts that provisions a Kubernetes cluster on AWS, Google Cloud, and other public cloud providers. My demo is running on AWS Cloud. So as you see in the box to the right, this box, kops creates the AWS resources like the EC2 instances, EBS volumes, security groups, etc., and then installs a Kubernetes control plane on it. The Kube API server is exposed via load balancer service, which creates publicly accessible Elastic Load Balancer, and you can interact with your Kubernetes cluster via this ELB by running kubectl on your development laptop. So this is what is shown in this box on the green. Now, Ray itself is installed as a Python package and is not Kubernetes native. That is, it doesn't come with an out-of-the-box Kubernetes integration. So for running Ray on Kubernetes, I use KubeRay, which is an open source toolkit that lets you run Ray applications on Kubernetes. KubeRay has been developed by a collaboration between Microsoft and ByteDance. And it uses the popular operator pattern to create and maintain a Ray cluster custom resource on the Kubernetes cluster. Again, if you're not familiar with custom resources and operators, I recommend looking them up in the Kubernetes documentation. So as shown in the boxes in the light purple, Ray cluster has three components: a Ray head group here, one or more worker groups, and a service that exposes the Ray dashboard and the Ray client on port 8265 and port 10001. And you can specify the parameters of the Ray head and worker groups and your Ray cluster custom resource YAML file. And then you can connect to the Ray cluster using the public IP address of one of the nodes on your Kubernetes cluster on the port that port 1001 is being mapped to. And then you can visualize the dashboard the same way using the destination port mapping for port 8265. And this is one of the features that I really love about Ray, the fact that you can connect to a remote Ray cluster and run remote programs all from your development laptop. This is like super, super convenient. Another way to connect with your Ray clusters using a jobs API, which I have not tried, but I just wanted to mention that. Now, then if you destroy and recreate the Ray cluster, the destination port maps will change, and because they are allocated randomly from a port range. So to avoid changing the port number of the dashboard every time you recreate the cluster, you can also add an egress rule, which is what is shown here, that will expose the dashboard via the ELB on a predefined path. So, and the Ray client, so one issue with this is that you cannot do this for the Ray client, unfortunately, because Ray client uses gRPC, and the Nginx egress does not seem to play well with supporting gRPC the way it is used in with Ray. At least I couldn't get this to work. And yeah, so maybe I can come back to the architecture later if there's more time. But let me move on with the rest. So in this slide, we'll go over some of the Ray concepts that we will be encountering repeatedly in the rest of the presentation. So tasks are arbitrary functions to be executed asynchronously on separate Python workers. An actor is basically a stateful task. When you instantiate a new actor, a new process is created, and the members of the actor are scheduled on that process and can access and mutate the state of the actor. Now, tasks and actors create and compute on objects, and these objects can be located anywhere on the cluster, which is why they're called remote objects. And remote objects in Ray are referred to as by object refs. Then remote objects are cached in Ray's distributed object store, which is also called the plasma store. And we'll be talking about the distributed object store a lot. So an important thing to understand is that there is one object store per Ray node. There is no global object store, which is why Ray used the term shared object store. And if an actor or task is running on a node and needs a piece of data that is not located in that actor or task's object store, then that data needs to be replicated from where it is located to wherever it is needed. All right, so moving on. So now we'll apply these ideas to downloading the speech-to-text model in our speech-to-text application. And in the next few slides, we'll consider two scenarios as laid out here. So looking at the scenario on the left, the first scenario is the object store replication from one plasma store to another. And in this scenario, a download model actor downloads the speech-to-text model from S3. And this model is then scattered to the other actors that use the model for performing speech-to-text on audio files. We'll call these actors as process actors. The process of scattering requires replicating the model from the object store of the download actor, like this one, to the object store of the process actors, and then into the actor's process memory, as you see here. So we'll be analyzing the bandwidth of this replication for several cases, such as when the download and the process actors are on the same EC2 instance versus on different instances. And then in the second scenario, laid out here on the right, the speech-to-text model is downloaded directly by each process actor from S3, and we'll be analyzing the bandwidth of this data transfer. And just as in the first scenario, we'll consider several cases, such as when the actors are located on the same EC2 instance versus when they're located on different instances. So moving on. So this slide outlines the four cases that we will be considering for the first scenario, which is the object store replication from the plasma store. So the first case, which is also our base case, is when there is a single download and process actor, and they're scheduled on separate EC2 instances. And the objective of this analysis is cross EC2 instance data transfer, because data is being replicated from the object store of one actor to another actor, and these two actors are scheduled on separate EC2 instances. Case 2 involves a single download actor and multiple process actors, each running on separate EC2 instances. So here, in addition to the cross-instance data transfer latency, we will also be able to analyze the object store read parallelism, because the data is being read from the object store of one download actor simultaneously by multiple process actors. Case 3 involves a single download actor, but multiple process actors running on different pods on the same EC2 instance. And now, because each actor has its own object store, the data still needs to be replicated across object stores, but this replication happens on the same EC2 instance, avoiding network hops. And so intuition would suggest that this should be faster than the cross-instance data transfer. And we'll see if this intuition is indeed true. And finally, case 4 involves a single download actor and multiple process actors running on the same pod. And because actors run on separate processes, in this case, data can be copied directly from the process memory of one actor to the other without the object store being involved at all. And again, intuition suggests that this should be even faster than the previous cases. And we'll see again if this intuition is true or not. So the overall theme here is that as you go from top to bottom, the locality, there is increased locality between data and compute, because the source of the data is located progressively closer to where compute occurs. Okay, so now we'll talk about the first case that we discussed in the previous slide. And so this is where we have a single download and process actor, and they're scheduled on separate EC2 instances. So the download actor is running on instance 1, the process actor is running on instance 2. So this case lets us measure cross EC2 instance data transfer latency, because this transfer is happening across EC2 instances. And as the table shows, the data transfer bandwidth for this case is roughly 140 megabytes per second. And this is our base case. So now here, case 2 involves multiple process actors on separate EC2 instances. So here there is a single download actor that downloads the model from S3 and then transfers the model data to the object store of that pod. And then this data is being replicated to multiple process actors running on separate EC2 instances. So like this shows there could be n of these actors, and each of them are running on separate instances. So as I said before, this scenario measures two things. One is data transfer across multiple instances, because the original model data was downloaded to the object store on this instance, and this needs to be replicated to the object stores of the process actors that are running on these other instances. And then secondly, parallel data replication, because the process actors are all running, like all of these actors are running at the same time, and the data is being read from the object store here, and this is being read simultaneously by multiple process actors. So this also lets us evaluate like parallel data reads. And we'll do this for varying number of process actors from 1 to 5, and I'll be showing the results in the next slide. So here are the results. So here we'll look at the change in the data transfer time as we increase the number of process actors from 1 to 5. And each process actor is scheduled on a separate EC2 instance. So as the number of process actors increase, the volume of data that is being transferred increases proportionally, because the speech-to-text model is being replicated as many times as the number of process actors. So we'll expect the data transfer time to increase with the number of process actors. Now the graph shows that while the transfer time, which is like shown in this this like lighter color graph, that while the data transfer time does indeed increase, the increase is not linear. So this is the line, the dark graph is what it would have been if the increase had been linear. So this is telling us that some parallel data read is indeed occurring. And the bar chart here on the right shows the beginning and the end of the data transfer for each process actor when the number of process actors equals 5. So that's why you have 5 charts here. So you can see that each data transfer operation begins at the same time, but finishes at a slightly different time. And the total data transfer time is reported as the time when all the process actors have finished the data transfer. And like one final note is that the transfer time here includes transferring the model data only, not running the model on the audio file, which is purely used for validation. And again, as you see, the data transfer rate here is a lot higher than what we had earlier. Again, showing us that some parallelization is indeed happening. So this slide shows the same analysis that we saw in the previous slide, but for previous versions of Ray. And as in the Ray Summit, Ray 2.0 was announced, and this is showing the same analysis as we saw earlier for previous versions of Ray. And as you can see, the data transfer bandwidth here stays constant, and the increase in data transfer time as the number of process actors is increased is nearly linear, which is much worse than what we saw in the previous slide. So this tells us that the parallel data replication has been significantly optimized in Ray 2.0. Okay, case 3. So this scenario looks at the data transfer speed when the download actor and the process actors are scheduled on different pods on the same EC2 instance. So this lets us evaluate object store replication speed when the object stores are located on the same EC2 instances versus what we saw earlier, where the actors were running on separate instances, right? So we will also look at multiple process actors, which will also let us evaluate parallel data replication. And again, we expect that the data transfer bandwidth is higher in this scenario because the data is staying local to an EC2 instance. And this is indeed borne out by the results. As you can see, the bandwidth is higher when the number of process actors is 2 versus what we had seen earlier when the actors were running on separate instances, indicating that parallel data read is supported as well. And again, like all of this is running on Kubernetes. So I also wanted to show like a screenshot of a kubectl output. So here you can see that the pods in question. So this is showing the pod IP address, and you can see that they are indeed being sort of assigned to the same EC2 instance, the 172.20.60.49. And we'll look at how to do this a little bit later in the presentation. And then finally, case 4, this scenario looks at data transfer when the download actor and the process actors are scheduled on the same pod, and each actor is running on a separate process. And to make this happen, we also have to make sure that each pod has enough CPU and memory resources so that the actors can be scheduled at the same time. So the difference between this scenario and the previous one here is that the data replication doesn't have to go through the object store at all. Rather, the data can be copied from the process memory of the download actor to the process memory of the process actors directly without the object store hop. And again, we'll look at like multiple process actors, which also lets us evaluate parallel data read. And again, we expect the data transfer bandwidth to be the highest in this scenario because the data is staying local to the program itself. And this is again borne out by the results, because you can see that the data bandwidth is significantly higher than what we have seen in the previous cases. This is a screenshot of the Ray dashboard. So this indeed tells us or shows us that loading the model from the object store and downloading the model, all of these actors are running on the same node. And again, we'll look at how we can actually make it happen. Like, how do we force actors to be scheduled on the same pod? All right, so a quick aside here. Here we'll talk about, as Jules mentioned, Fred Rees from IBM had this really incredible talk on zero copy model loading. So here we'll look at how what we have been discussing here connects with what Fred had to say. So Ray has a feature where all Ray workers on the same node can read an NumPy array from the object store without copying it into the process memory. So Fred showed how this feature can be used to run inference on a PyTorch model 7 times faster by avoiding this expensive copy operation, right? So it is a really compelling and well-deserved talk, a well-delivered talk, and I encourage all of you guys to check it out. So what Fred Rees was talking about is this part. So how do we avoid copying data from the object store to the process memory? What we are talking about here is object store replication, like this green arrow, plus the copying data from the object store to the process memory. So what Fred was talking about applies only when the model data is available in that node's object store. And he also makes this point in one of the blog posts that in order for the model to load instantly, a copy of the serialized model and its weights need to be in the local node's plasma shared memory segment. And if that is not the case, then you will have to wait for that data to become available. So I just wanted to talk about what the subject of this talk, how that connects with what you will see in Fred's talk. All right, so now we'll move on to the second scenario, and this is here the speech-to-text model is downloaded directly by each process actor from S3, and we'll be analyzing this bandwidth. So here now we'll call our actors download plus process, because each actor is now also responsible for obtaining the S3 credentials, creating a photo session, and then downloading the model from S3, as well as running the model on a sample audio file. And we'll consider just the model download time, not the time taken to load the model in PyTorch and running it on the speech sample, so that we can do an apples to apples comparison with the scenarios that we have discussed previously. And we'll consider several cases, such as when the actors are running on pods located on different EC2 instances versus when they're running on the same EC2 instance. All right, so moving on. So to avoid repetition, I'll just talk about cases 1 and 2 together on this slide. So this table shows the change in the data download time as the number of download plus process actors is increased from 1 to 5. So each actor is scheduled on a separate EC2 instance, and you can see that the download time stays nearly constant, right? So we vary the number of actors from 1 to 4, and the download time stays nearly constant, around 5.4. Even though the amount of data that is being downloaded scales linearly with the number of download and process actors, because as each process actor is pulling its own copy of the speech-text model. So the total amount of data that is being downloaded increases linearly as you increase the number of the process actors, but the total download time stays nearly constant. So this is telling us that S3, AWS S3, supports parallel data reads very effectively. And the Ray dashboard here shows like 2 download plus process actors, which are running on separate pods that are labeled like worker C and worker F. The one point to note here is that the object store is not being utilized because the model data is directly copied into the process memory of each of these actors. And then, okay, so moving on. So here we analyze case 3, and we vary the number of download plus process actors from 1 to 6, and we schedule these actors on the same EC2 instance. So previously, the download plus process actors were being scheduled on separate EC2 instances, and here they're being scheduled on the same EC2 instance. So each actor, as before, downloads the speech-to-text model independently from S3. Now, since the data must pass through the network interface of the EC2 instance where these actors are running, as shown here, and this interface has a finite bandwidth, we can expect that this download time will increase as you increase the number of download actors. And this is because the amount of data that is being downloaded increases in direct proportion to the number of actors, right? So the graph on the top left here shows that this is indeed the case, but the rate of increase has a slope that is less than 1, so it's around 0.3, meaning that the download time doesn't increase in proportion to the number of download actors. So if it had increased in proportion to the number of download actors, then you would have seen something that looks like this graph, the one in the dot color. So it does increase, but not linearly. So this tells us that when actors are scheduled on the same EC2 instance, object store replication is more efficient than independent data downloads from S3. Okay, and the kubectl output here shows that the 6 pods, so each of the actors are scheduled on separate pods, and this is showing you the pod IP, and they're all running on the same EC2 instance. So this tells you that all of these 6 pods are scheduled on the same instance. Right. So moving on. So this is very similar to the previous case that we just talked about. The only difference is that the download plus process actors are running on the same pod. So whereas before, each actor was running on different pods, which were scheduled on the same EC2 instance. And again, I show the data download time for the number of actors going from 3 to 6. So the trend is very similar to what we saw earlier when the actors were scheduled on separate pods. So you do see an increase, but it's not a linear increase, which is what is shown in the yellow graph. And also, as we saw earlier, the data is copied directly to the process memory of each actor without the object store being involved. And then here and in the next slide, we'll talk about how we can use the features provided by Ray and native Kubernetes features to schedule pods on a certain EC2 instance or a group of instances, and actors on a given pod or a group of pods. So let's begin by talking about scheduling actors on a given pod. So this can be done by using a Ray feature called custom resources. So custom resources can be defined in the worker specification section of the Ray cluster YAML as a key value pair. So that's how this looks like here. The value is the number of custom resource the worker can support. So 2 in this case. And this can be used to limit how many actors can be scheduled on this pod. So for example, here, we are saying that no more than 2 actors that specify a worker pod B can be scheduled, right? So no more than 2 instances of this F1 task can be scheduled on this pod. And then also note that you also need to specify or ensure that the pod or the node has sufficient CPU and memory resources to run the actors concurrently. If you don't do that, then your actors will crash because of out of memory or other resource errors. So like Ray cannot predict what is the total peak CPU or memory utilization of the task or the actor that is going to be running on that pod. So you have to make sure that you provide like the right CPU and memory resources and limits in the worker definition, so that the peak memory or CPU utilization of a task or an actor like stays below what the CPU limits are. Okay, so with that said, now let's look at how we can force pods on certain instances or group of instances. So this can be done by using standard Kubernetes techniques, such as using node names, node affinities, and tails and tolerations. So node name allows you to specify the name of the Kubernetes node that you want a pod to be scheduled. Again, and if the node doesn't have sufficient resources, the pod will stay in a pending state. So I show that here. So you can just like specify that schedule this pod on this particular node. Or you can use a Kubernetes concepts called taints and tolerations, which I'm not going to go in detail, but just suffice it to say that there are like a menu of techniques available that lets you sort of force Kubernetes to allocate certain pods on certain nodes. And I'll just quickly go through a couple of other techniques. So you can, like in the previous slide, we saw how we can schedule actors on specific pods. Another way to achieve the same outcome is to specify the resources directly in the task and or actor definition. So like here, I can just specify directly in the sort of the decorator for this function that my method needs 5 gigabytes of memory. And Ray will automatically schedule this task or actor on an instance that meets those requirements. And then Ray also offers placement groups that allow users to atomically reserve groups of resources across multiple nodes, which can then be used to schedule Ray tasks and actors, which can be packed as close as possible. So I have not tried this in my demo, but just wanted to say that Ray also offers other tools and techniques to make all of this happen. All right, so finally, these are the conclusions. So for map tasks, tasks that perform a repeated operation on the same data or shards of data with a medium, let's say less than 10 mapping index, object store replication is more efficient. This is because actors can be scheduled on a small group of EC2 instances with multiple actors on the same instance and benefit from the moderate level of read parallelism supported by the object store. So this is what you see here. Like when you have a small number of actors, then you are better off using the object store. And a couple of other points to note is that there is a major improvement in parallel read bandwidth in Ray 2.0. Now, since the object store comes out of the box with Ray, this also eliminates the need for setting up a distributed object store, such as a network file system or MinIO or a multi-mount EBS volume. And then finally, using the object store, the data stays local to your cluster. So this also minimizes the risk of any data leakage, right? So if you, for example, like if you had to set up a network file system or EFS or something like that, your data will be going back and forth from your cluster over to your network file system. But by using the object store, you also you get better data privacy and security because all of your data transfer stays local to your cluster. Now, point number 2, for tasks with high mapping index, parallel reads from S3 may be more efficient, and this is because S3 offers really great read parallelism. However, when the data size is small, then object store replication could still be more efficient. And then secondly, you also need to consider the latency of obtaining S3 read credentials and creating a Bodo session. Because anytime you are like pulling data from S3, you have to obtain the S3 credentials, you have to create a Bodo session, which is not required when you are using replication from the object store. So when the data size is small, even if you have a large number of tasks, then using this object store could still be more efficient. Then point number 3, it helps to locate the data source and the data consumer as close as possible to each other. For example, on the same EC2 instance, or even on the same pod. And then finally, you must anticipate the peak CPU and memory use and schedule actors and tasks on pods that have sufficient resources. Otherwise, your actor and task will crash. And Ray offers several methods to achieve this. And we saw several of these methods previously in the presentation, such as specifying the resource specifications for your actors, specifying custom resources, and so on. And then, like in closing, I also wanted to mention a couple of other Ray features that I really like. First of all, I really like the distributed computing abstractions that Ray offers, things like tasks and actors. I find them really well architected, and they map well to my own mental model of what is going on. With some other tools, particularly Dask, I just found their abstractions like hard to conceptualize. I love the support for distributed queues, which is something that Dask doesn't have. And I've used distributed queues extensively in my demo. The Ray Kubernetes integration is really nice. So Kubernetes is a really powerful, but also a really complex system. And using, like combining that with Ray, which is also a really powerful and complex system, can be really tricky. And the Ray Kubernetes operator strikes the right balance, abstracting some of the really low-level details, but still providing developers enough flexibility and power. And then finally, I love using the Ray client to connect to the Ray cluster using PyCharm, which is my favorite IDE. It makes the remote development almost as easy as if you were developing locally. So yeah, I love using Ray client. And that concludes my talk. And so thanks for listening. And I don't know if I have any time left, but if I do, then happy to take any questions.
Thanks, Ankur, for very detailed, very quantitative analysis of your experiment. There's any questions? I don't see any questions on the chat. I was wondering if the chat would disable. We approved that it's not. The Q&A is open, so if you guys have any questions, feel free to put it in there. But I just have a question off the back. How big is your model? I mean, are we talking about in megabytes or?
Yeah, so it's about 600 megabytes.
600 megabytes? Yeah. Okay.
Yeah.
And is this a PyTorch model, or is that a TensorFlow?
It's a Hugging Face.
Hugging Face. Okay. That's the one.
Speech to text transformer model. Yeah, should have mentioned that. Yeah.
Yeah.
So you can download this from Hugging Face speech to text. It's a pretty standard model that is used in a lot of different benchmarks.
So when you're putting the model on S3, when you're putting the model in the object store, you're using the APIs to do a Ray put and Ray get. Is that how you're
that's right?
Doing
Yeah.
It? Okay.
Yeah. So you I load the model files from S3, and then like in my download model actor, I just like pass a reference to the. So I create a dictionary with like key value pairs with the values being the loaded model files, and then I return back basically this dictionary, and then in the process actor, I pass a reference to that dictionary, and then when I call get on that object reference, then Ray automatically does the object store replication. So it figures out that the actual data lives in the object store of the download actor, and then it copies it over to the object store of the process actor, and then copies it further into the process memory of my process actor, so that now the model becomes available for use.
So in terms of, I mean, I saw that you actually use the custom resources on the YAML file, but as you mentioned, you can actually use the same thing in placements groups. So I don't know if you actually tried it, or maybe a good experiment to see if it makes a difference, because it figures out the best way to the locality to do that. So I think experiment 4 could be try to use placement groups. And let me see if I have any questions. Just a general comment. I wonder if you had actually used Ray Air to be able to distribute. There's no data involved because you already have a model, so you're not doing a training or not doing tuning. but I was wondering if you could actually pre-populate the model using Ray data to do the push, just like Fred did. You know, Fred was able to actually pre-populate some of the models, and that way, where the task was scheduled, it was almost zero copy because it was using the NumPy zero copy array to go straight into it. But that would be
that's right.
Yeah.
Except that, like, I'm also using Ray auto scaling, which is another really powerful feature of Ray. So I have like a min-max number of replicas set up in the configuration for the pod where the speech-to-text actor is running. And so when the application starts running, the autoscaler detects that, like, I'm trying to create 6 speech-to-text actors, but there is only, because the minimum number of replicas is 3, it starts off by like just 3, like a space for just 3 actors. And then when it sees that it needs more room, it creates like it spins up 3 more pods, and then the speech-to-text actor is then allocated on those pods. So the model is not like you don't know a priori how many actors you would end up running as autoscaling kicks in. So like pre-warming the actors would not work in that scenario, where autoscaler decides how many actors would be running as your application scales up and down.
Yeah.
Does that make sense?
Yeah. So in terms of your development environment, you actually were using, did you say you're using Jupyter Notebook and you're using Ray Client on your local machine, and you were just connecting to your head node, correct?
I'm not using Jupyter Notebook. I'm using PyCharm. I'm not a big fan of not a big not a fan of Jupyter Notebook whatsoever. Yeah. So the way, so it's what you can do is when you create a let me just quickly go back to the architecture diagram. That will make it easier to explain this. Yeah, so when you create the Ray cluster, you can specify what the type of the service that is created. So this can be a cluster IP service, a node port service, or a load balancer service. If you create a node port service, then Kubernetes will automatically map the ports that are exposed on the service to a destination port, which can be accessed on any instance in your Kubernetes cluster. So then you can, in your driver code, which is running on your local computer, you can simply connect to you can pick the public IP address of any of the nodes on your cluster, and then use the destination port in the service description, and then you can connect to your cluster using that. Now, as I said before, now if you delete and recreate the Ray cluster, because this destination port is chosen randomly, this port will change. So it would be nice if you could create an ingress, and then you can create a prefix, right? And then the ingress controller will automatically detect that a new service has been created, and will automatically like connect to that service. And you can use a fixed like URL for connecting to your Ray client. But because the communication with the Ray cluster happens over gRPC, I found it tricky to expose the gRPC connection over ingress. I could do it quite easily for the Ray dashboard. So I can like, access the Ray dashboard using the ELB of my Kubernetes cluster and just using like Ray dashboard. This is the prefix that I specified in my egress configuration. But it would be nice if I could do the same thing for the Ray client as well. But I couldn't get that to work.
Okay, I think that's all the time we actually have for the question. Thanks a lot, Ankur, for your very detailed analysis of that. We'll move on to, I think there's one question, but we can actually, you can go to the chat and answer it. Is it possible to do something similar from PyCharm to AnyScale workspaces? I can answer that question. Yes, you can. All you have to do is in the Ray init, you actually provide the AnyScale : the name of the cluster you actually want to connect to, and it will actually connect with that cluster. So you can do pretty much the same thing as you can do it for the open source, except that the URL actually has the AnyScale : the name of the workspace, the name of the cluster that you actually have it, and it will connect automatically to the head node. The only thing you actually need is the Anyscale pip install Anyscale client on your machine. You should be able to do that. All right, Ankur,
Yeah.
thanks a lot. If you can stop sharing your screen, and I'll have Simon come in and.
Yep,
there
I
he is.
stopped sharing.
Okay, brilliant. Yes, Simon is there.
Sounds good. Sounds good. Let's should we dive straight into it then? Cool. Awesome. All right, I'll get started. So hi everybody. So thank you for sticking here still with our second talk. So will actually be this is a talk we have done a month ago at the Ray Summit, but here I'm here to essentially to give you some updates and discuss this again about what's new in Ray Serve in Ray 2.0. So before I get started, so I will of course give you an overview of what Ray Serve is about, what problem is it trying to solve, and then in particular I'll highlight 3 major features that has been in the works for the past few a year and leading up to our 2.0 release that you can try out today. So to get started with what is Ray Serve, what problem are we trying to solve? Ray Serve, if you look at the Ray ecosystem, in particular, Ray Serve is a component here in the Ray AI runtime, where it is built on top of the powerful primitives of Ray core and then it's parallel to other Ray AI runtime libraries like Ray datasets, Ray RLib, or Ray Tune, where Ray Serve takes care of the job of take a trend model and make sure it can run it in production with live 24/7 services and traffic. Now, so in one sentence, right? What is Ray Serve? Ray Serve is a flexible, scalable, and efficient compute for online inferences. In particular, by building on top of Ray, it brings a scalability and sort of a low latency perspective, as well as being extremely efficient and cost saving for your workload. Ray Serve has a first-class support for multi-model inference. This is what we observed after working with many different use cases, as well as many users that use Ray Serve to see that it had to build a modern machine learning application in real world. You actually need multiple models working together to solve a single problem. Additionally, because by building on top of Ray, Ray Serve is Python native, you can very easily mix and match your business logic with machine learning. And this will help you to visualize code, debug, and visualize everything in one place. And in particular, this first-class support for multimodal inference will be a big feature in 2.0. We'll discuss it a little bit later. But to prefix this, we'll contextualize what we're trying to do in this kind of very much what we have seen a real-world example, right? Imagine we're trying to build this real-world machine learning application. Well, let's take an input image, right? And they just call it some sort of product classifier or product tagger, where we want to detect the image, give it some confidence score, right? And then maybe add some metadata and segmentation of the pixels. On the surface, to build this kind of application, it might just be very simple, but actually if you wanted to make it for real production, actually a lot of cases you need to add several components to it, which will make the whole application fairly complex. To start, the image might be big, and there might be a lot of people sending image to the service. This means a more practical solution will be to upload the image to some data lake like object store like S3 first, and then so it will be useful for archiving later. And then, so the first component of our application might be a downloader that would retrieve the object. After that, we need to do some CPU intensive pre-processing on these images so that they can be properly turned from JPEG into like tensor formats. And after that, we'll probably send it to some image classifier. But a lot of cases, image classifiers are specialized for the categories because this is the only way to boost sort of the model performance and accuracy. So right here, we'll probably have a class of like a group of classifier, and we'll select one of them for our prediction. And additionally, our business also requires us to not just classify the image, but also detect, for example, where exactly the object is. So therefore, we'll want to also, at the same time of sending the tensor to the classifier, or maybe we want to send it to a detector. And in the end, we want to combine all this into a structured output that front-end application can understand. So this is it might seem a very contrived sort of content understanding application, but this is really a distillation of what we have seen from a lot of production application today. So if we get to deploy this into production, let's look at some requirements. First of all, of course, this has to be a live inference service. That means the latency should be minimized as well as the throughput should be maximized. Additionally, machine learning models are incredibly expensive, right? A lot of cases they have low throughput. This means we will try to use fine-grained resource control such that like our resources efficiently utilized. A lot of cases, if this model is rarely used, we want to assign fractional resource constraint to them, like fractional CPU or GPU, in order to pack as many models as possible onto a single machine. And furthermore, we want to figure out to have a programmatic API so that it is easy for you to iterate and build this kind of end-to-end application instead of like, for example, battling Kubernetes to figure things out. But once you have made it ready for production, the move to production story should be rock solid, right? It cannot just be, after all, it's no longer just running a simple Python script anymore. This service needs to run 24/7. And in order to satisfy this, like a common solution here is really just to pack everything together and use the existing web microservice deployment models for this, right? The idea being that maybe we can build a fast API server, and then within it, we can pack all the steps and then all the models into the same application in the same handler, and then pack everything into a Docker container and scale it out in a conventional way of deploying a web app. This approach definitely works, right? In fact, it's the first approach what people try to do today. However, it has several downsides. First of all, it's really hard to scale the models independently. So in the image, for example, it's hard to separate the Python from the TensorFlow, from the PyTorch. And then, for example, a lot of cases, maybe your application is bottlenecked by a single component, but there's no way to scale that out. You have to scale the whole application as a unit. And additionally, this approach can involve high latency, low throughput, and in particular, because of the inability to scale the bottleneck, is often very costly because you have to scale other parts together. Now, people have looked at this and it's like, wait, we can break it up, right? You can, of course, put certain components in their own image, in their own microservices, and then move the other model into the other microservices. In particular, we can see these as sort of the model as container approach. And as identified by the YAML here, or the YAML icon here, you do have to deploy them separately and glue them together using some sort of custom protocol again to make sure everything fit well and can call together. It does allow you to scale the model independently using different resources. This is great, but however, the operational aspect of this, as well as the maintainability aspect of this, will be pretty miserable. The reason being that now you have to, for your single, very simple content understanding application, you have to worry about, at least right now here, we have seen 4 different YAMLs and keep them all up to date, figuring out how do they update together, as well as all that kind of a messiness come from directly working with Kubernetes API. So Reserve, on the other hand, is built differently. We have this kind of first-class support for multimodal inference that allow you to write a single Python program, use your favorite library and frameworks, and under the hood, it can scale across CPU and GPUs. Let's take a closer look at how would that work. So Reserve application in production, we should run it on your Kubernetes cluster. So the application typically consists of many different pods. And if you're familiar with Ray, this different pods are essentially different Ray cluster nodes. And then if you look at how we, for example, map the application to these to the different pods, we can put a downloader in one of the pods and the preprocessor on another, so they kind of balance out, right? And maybe all the image classifier fits on one pod, therefore put all of them with shared fractional GPU on there, as well as image detector to balance out on a different pod, and then in the end combine them together using some sort of components there. And this application, looking at it, is transparently scheduled and placed onto different Ray cluster node. And furthermore, we can have a clear understanding of, for example, how is each component using resource. And in particular, for example, we can assign fractional resource to like the image classifier so that all three models will occupy only one GPU. So what you can see here is really allows you to use a single Python program that you can develop and test locally, and then you just deploy the hosting on a cluster of machines and pods such that it can be as easy as develop a single program, but also as powerful as scaling everything out separately. And in RaySearch, this is the problem we're trying to solve in RaySearch, right? In RaySearch 2.0, we want to take a step further to make sure that in production, RaySearch can work for you. And this means we want to add we added a lot of feature for great UX for a flexible model composition, as well as improved autoscaling to help you to save cost. And furthermore, we have added a lot of production hardening features that with a focus on Kubernetes as a de facto platform that deploys your application on there. So let's take a look one by one. To start with, we have created a brand new model composition API that will help you to build this kind of complex business application on top. But if you look at the requirement, what you need to build here is that such sort of API needs to be very flexible. You need to satisfy constraint like you need to work with different models, different framework, and you can add arbitrary business logic, as well as it should be very easy to develop and test locally. And then when you're running in production, it doesn't just waste money and have a lot of high overhead. So our model composition API is built with these requirements in mind. In particular, we built a first-class support for what we call a graph of served deployments. And then it can essentially, by building on top of existing features, it has a full flexibility of it that allow you to also configure and scale each module independently, as well as to orchestrate the computation. You can let's take a closer look at some snippets of code that will exemplify this. For example, if you want to take a very simple look at how do we bring two models having to chain together. On the top here, we're just creating the two models. These models under the hood can scale independently, have many different replicas. And then to orchestrate this compute, we just use simple Python code right here as a declarative way of saying, well, given the input come in, I want to pass it to model 1. And then given the output of model 1, I want to pass it to model 2. And that's it. There's no complex YAML configuration here. And you just specify the data flow using Python. Same goes for what if we have the input broadcast to different models and combine them together. And this is essentially almost minimal change to our previous example. Instead of passing the M1 output to M2, we want M2 to directly take the inputs and then combine them together using a combiner node. So in this case, as you can see, the input is actually broadcasted together to both M1 and M2, and the prediction will run simultaneously at the same time, such that your latency is minimized. And then we can go even further with more complex patterns. For example, here we have model 1 and model 2, and you can create some selector that will dynamically select given the input. So we'll call selector.forward.bind with the input here to choose under the hood which model to send it to. So we have this kind of flexibility and also expressibility such that you can build arbitrary complex application with very few lines of Python code. So essentially, we can bring all of this to our simple, to this kind of, this looking like complex application, but you can really write it very easily. And there's actually a deep dive talk I'll mention later that dive into exactly how you implement each part of this in more detail. But for now, let's take a little bit closer look at yet a different feature. Before that, let me summarize this, right? Again, this is why I said allow you to write your model as ordinary classes. It gives you the flexibility to compose them into Python, as well as you can run it on a laptop and scale independently in production. Now, let me move on to the exciting topic that will help you to save money, in particular in production. That is, how do you do autoscaling for machine learning models? So the problem here is that machine learning models are very compute intensive, but any given time, a lot of models are not used. And it's going to be very tricky to tune the hardware utilization, because at any given time when a request hits, it will try to use as much hardware as it can. And then, at idle time, it will just use 0. So it's unlike traditional web services, where the CPU and hardware utilization scales sort of in a continuum, machine learning utilization curve looks more like just discrete, right? When a request hits, you'll hit 100% and then drop immediately. And this is actually a common case. And additionally, making it work for multiple models in production together is even harder in this scenario. So in Reserve, we have provided in 2.0 an advanced autoscaling feature that in particular scale a very fundamental workflow called scale to 0. It means that when your application is not used for, say, 5 minutes, we'll make sure to destroy it and destroy the model and deallocate the memory and release the resource. And only when the traffic hits, we'll bring it back up. This will help you to save costs drastically. And instead of using sort of hardware utilization metrics, we provide a very intuitive API allow you to configure the request queue length that would directly inform you what's the expected latency of query in worst case scenario, and how that directly map to your business objective SLA. And additionally, this API is fully compatible with the model composition API I mentioned before. This means you can do advanced autoscaling that will help you save costs, even scale to 0 from sometimes, with this kind of complex 5, 10, hundreds of model in production scenario. So let's bring back the example and let's see it in action. So for example here, because we have dynamic dispatch, we're choosing different classifier for our different, for given different images, for example, right? So right here, we can observe, Reserve can observe image classifier is getting a lot of requests. Image classifier 2 is only getting 1, and image classifier 3 is not getting any request. And very quickly, we can detect, well, for classifier 1, the queue size is much greater than the target queue size have specified and configured by the user. And therefore, we drastically scale out classifier 1, given some metrics, by adding the replicas. And then now the request loads evened, and now requests are no longer waiting. For classifier 3, we look at it and see, well, there's no request for some duration of time. We'll remove this replica and free up more resource. So that, for example, if classifier 1 is getting even more popular, we can essentially leave the resource to classifier 1. And in short, is that our autoscaling API is how we iterated to find out the best API for you to just adjusting a few parameters without profiling or update your model to exactly intuitively match that with your business application. And additionally, scale out, scale to 0, and is fully integrated with model composition so that every feature works extremely well together. And additionally, last but not least, I'll mention the work we have been doing for production hardening. So of course, online inference, by being online, it means we need to make sure it's solve a lot of operational problem, right? When you are updating your application, we need to make sure we can update without downtime, as well as we need to make sure when anything in the system fail, we can handle it gracefully, but without paging you, and then paging you as the operator or the SRE or the ops person, and they can transparently recover. And then, of course, when things does go wrong, monitoring, observability, and alerting is absolutely critical. So what we want to do here is to make sure to bridge the operational benefits of Kubernetes, as well as a full flexibility, user experience, and efficiency of Reserve together to help you to essentially run it in production without much hassle. And let's take a look at one of the features I built is called Kubernetes, is a Ray service operator in the KubeRay project. So when you are developing as a application, as here in the sort of the laptop, you can continue to iterate locally. And then if you want to, when you bring it to production, we have a new feature called serve build, allow you to generate a YAML configuration file from this from your application. And then you can directly call kubectl apply to apply this to the Kubernetes operator. And then the Kubernetes operator will create, update, and monitor several reserve cluster, which is composed of Kubernetes pod. That will make sure you'll run live continuously. And if any component of it fail, the Ray service operator is now a component that will make sure it can recover and your application will continue to run. Additionally, the Ray service operator also continuously perform health check on the Ray service to make sure that your application is always up. If it is not up, if it detects health check signal failures, it will kill the cluster and start it again. So, and then in short, this Ray service operator help you to perform zero downtime upgrades. It can do the health checking and recovery properly, as I mentioned, as well as by being fully integrated with Kubernetes toolings, you can easily call like kubectl apply so that you don't need to install additional tools. It's just using the same old Kubernetes API. And then another feature I have built working together with other teams here is what we call GCS fault tolerance. Prior to Ray version 2.0, Ray as the general framework actually have a single point of failure. That is what we call GCS, Global Control Store. And this component store all the metadata and scheduling information for your Ray jobs. And when this component crash for some reason, right, or the head node crash, then the entire cluster go down. But in Ray 2.0, Ray can actually now recover from GCS failure. This means when the head node crashed or the GCS crashed, worker node, since running on worker node can continue to run, and when the new GCS is restarted, or head node is brought back, then this whole cluster is recovered and business as usual without interfering at all. So this operation itself is handled automatically by the Kubernetes operator, but of course you can also manually try to bring the head node back and GCS back and observe the same effect. So, and the important piece here is this actually increases our availability by making sure that reserve application can continue to serve traffic when the head node or the GCS goes down. And in particular, in one of the later deep dive talk, we actually show that we have done like a very stressful chaos testing where we kill a random node every few minutes. And this is a very stressful workload while maintaining a 99.99, 4 nines of uptime. Cool. So to summarize, in Reserve 2.0, we actually add a lot of feature to make it very easy to put scalable machine learning in production. In particular, we added a first-class support for flexible model composition. We added a lot of feature for auto-scaling to make sure that it is help you to be cost efficient. Additionally, we'll have few components newly added, as well as the GCS fault tolerance feature to help you to really run Reserve on Kubernetes without worrying about it going down. And so I mentioned a lot of features today, and we actually have a lot of deep dive talk where you can go to Ray Summit website now, and then to check out, for example, how exactly do we do Reserve, like this kind of operator, and how exactly does it work, as well as we have a deep dive talk about the model composition API. And additionally, we have a deep dive talk about the GCS fault tolerance and like exactly under the hood, how does it work? And we can reason about the distributed nature of each component. And we also have different talks about how people from the community in particular, how they build question answering system on top of Reserve, as well as as Ankur probably mentioned before, this very exciting work about zero copy model loading, essentially allow you to instantaneously load a giant model into your Ray project and then get it running. So yeah, in short, that's pretty much it. You can check out reserve.org as well as all the Ray Summit website to check out more deep dive.
Thank you, Simon, for that wonderful talk. And I'm sure, as you mentioned, these talks are also available, more deep dives into what you actually referred to at the Ray Summit. So guys, feel free to go to the Ray Summit and check out some of these talks. One of the things that I was curious about was this one, the production hardened is only available for Kubernetes, correct?
Right.
For right now. Okay.
Yeah, right now. Yeah.
What are the plans for making this sort of available for other platforms?
Right. So right now we are only running this on Kubernetes because we have seen this is the de facto way of deploying live online services. However, we are getting notes from folks about, hey, we actually run EC2, and we have been looking into it and to see if there's opportunity of bringing that kind of feature in and or develop the feature together with the community. Yeah, if you have that request, please let us know.
Yes, and if you actually want to have these race of hardening HA available on clusters other than Kubernetes, do let us know, especially post something on either Discuss or file an issue, and I'm sure Simon will get on top of that. One final question. I don't see anything coming in from the community, but one final question was in the decorator for auto scaling. If I declare that and I've already deployed the particular model, but I want to change my scaling configuration, can that be done dynamically, or do I have to redeploy?
You can entirely do that dynamically, and then that's what sort of the YAML has been built here. Essentially, this YAML is built here for you can adjust it in real time without bringing down the application.
Okay, brilliant. So all I have to do is if I wanted to go from 1 to 10, I wanted to go from 1 to 5, I should be able to just change that YAML, and then it will automatically notify the deployment version of it to scale it down to 5 rather than 1.
Yeah, exactly.
Okay, I don't see any questions coming up, but thanks a lot for your diligence and staying up. And for those of you who actually stayed with us for a while, thanks a lot for joining us. And this recording is going to be shared with you along with the PDF of the files. And as I say, we have upcoming events coming up. Do let us know if you do want to talk. Let me know if you want to write a blog about your journey with Ray. Let us know. We are more than happy to actually share your journey with our community. And again, thanks a lot. Thanks a lot, Simon. And thanks a lot for the community who actually joined us today. So hope to see you in a month again. Bye. Cheers.
Thank you, everybody.
Stop recording here.